Hello, everybody. Thank you for your time and for your interest. I would like to warmly welcome you on our webinar for, at least for us, very fantastic topic AFM-in-SEM and the future of complex and in-situ correlative analysis. My name is Jan Neumann. I'm CEO and the co-founder of the Nanovision company. And together with my dear colleague Veronika Hegrova, we would like to introduce you briefly a Nanovision company and tell you about the key benefits and advantages of our product, applications, and fascinating AFM-in-SEM technology. I would like to also say a few words, a few technical words. So the first of all, webinar will be recorded. The second, all of you are muted, so you can try, but probably will or definitely will not hear you. And please be just aware there is about 30-second delay between our broadcasting and your watching, so we might be slightly delayed with the responses. With that, I would like to let me introduce you in few words the Nanovision and also the place where we are. So we are located in the Czech Republic, in Brno. We say we are in the heart of the Europe. And Brno is beautiful city where is the location of many universities and research institute. And we are quite well known for our long history related to development of electron microscopy. We are proud to say that we are a leading center of electron microscopy, and about 30% of the global production of the SEMs are done in Brno. We have also live microscopy community where the leaders in its field as the companies Thermo Fisher Scientific, Tesca Cell Holding or DeLong Instruments are a part of that. And so we are very happy that we can contribute together with several academics as the Brno University of Technology or Masaryk University or Institute of Scientific Instrument or SATEC. Together, we try to push the microscopy to the next level. As I mentioned, I guess you expect that our contribution is our AFM module for the electron microscopy. For scanning electron microscopy. And so we believe that merging of forces of AFM and SEM is an important role in the characterization itself. Our mission since the beginning is to create the unique tools on the top technological level which drive scientific discovery with significant impact. Other way around, what we like to do and what we are doing, we are creating the tools for you, for the scientists who can then make our world better. We do that via the cooperation. So within the last year, we have developed very broad range of the cooperations with the leading companies, but also the universities and research institutes. And together with them, we try to push the limits of the current trends in microscopy as a in-situ microscopy or analysis, multimodal sample analysis, and correlative microscopy. And we feel that we are able to contribute with the microscopy itself to some of the global challenges. And therefore, we see the opportunity to help to solve some of the issues like the energy storage or with the batteries or semiconductor on development of novel sustainable materials. Simply together, we are trying to break the limits of in-situ multimodal correlative characterization. This forces us, and actually it's our passion, to innovate. So in the last year, we have launched our second generation of our Lightscope, which is faster, lighter, and smaller. We have introduced to the market also the nano indentation module, which enables the quantitative mechanical characterization of the sample. We launched also the sample rotation module, but also we introduced and improved significantly advanced characterization methods, enabling to analysis using the MFM, KPFM, conductive AFM, etc. And last but not least, we introduced recently the CPEM Plus software tools, which is based on the artificial intelligence and enabling very precise and automated data correlation. Much more we plan to come in 2022, so stay tuned. We will come back. What I would like to highlight that Nanovision is not just the words, but mainly we are the people, and we are quite enthusiastic and maybe sometimes quite special. But together with cooperation with many students, we are very happy to have an opportunity to contribute to the microscopy. So if you like what we do and you would like to support our activities, so do not hesitate to join our community, to join our cooperation network and buy our product. With that, I would like to slowly pass the words to my dear colleague Veronika. She will tell you in more detail some key benefits and advantages about the AFM-in-SEM technology itself. She will talk about our unique correlative techniques, which we call correlative probe and electron microscopy. She will introduce or tell you more details about the Lightscope itself. She will present, I would say, fantastic application examples, and by the end there will be space for your questions and comments. With that, I would like to really encourage you to ask the questions, write the comments, and give your suggestions, because we need you to fulfill our company mission. So I would like to thank you for your attention. Enjoy the rest of the webinars, and with that I would pass the word to Veronika.
Thank you, Jan. I would like to start with the AFM-in-SEM, why we actually would like to combine these techniques together. So atomic force microscopes and the scanning electron microscopes are two of the most used and in fact complementary techniques for the sample analysis in the nanoscale. Nevertheless, since the principles with which we observe and using this AFM technology or SEM technology, they are quite different. AFM monitors the interactions between a probe and the sample surface, and it has very high resolution in that direction. On the other hand, scanning electron microscopy observes and analyzes the surface using a focused beam of electrons. So it has very good resolution in X and Y. So if we combine these two technologies, we can benefit from each of the technique. So if you imagine that we measure the three-dimensional topography together with the magnetic properties, and we combine it with 2D fast imaging and chemical analysis from EDS, we get much more information which we have from the same place. And so we have, if we imagine this solution as we see on the scheme, we have in situ sample analysis. We measure both techniques together at the same time, in the same place and under the same conditions. So we are able to measure complexly. We have the multimodal analysis, so we can understand better, and also it's easier to localize the region of interest, and it's not needed to localize several times in different microscopes. So we provide the scientists information about their samples, which are often unable to acquire, or it's extremely complicated. So let's have a closer look at these three benefits, so we will understand better. So as we have a look at the scheme, all measurements are done at the same time, in the same place, and under the same conditions. So here is the scheme of SEM chamber and Lightscope laying on the stage. So we don't need to transfer the sample and risk, for instance, of contamination during the analysis. Our scientific ambassador is Mark George Willinger from Switzerland, and he said nicely that Lightscope is like a Swiss Army knife inside your SEM. What it means that we add to the capabilities of SEM other modes from AFM. So we get more. The second was the complex sample analysis. It is a unique method of multidimensional correlative imaging, CPAM. I will be talking later about it. It can simultaneously acquire AFM and SEM data in seamless correlation into three-dimensional images. So if we have the topography, at the same time we measure the hardness of the sample with the material contrast from secondary electrons and with the EDS map. So as we see, we have from the same place more channels together correlated. The third one was the fast and precise navigation. It's extremely precise and time efficient. How to localize the area and the probe navigation using AFM-in-SEM, because SEM has wide field and very good resolution. So we are able to reach hard to reach places, and it becomes possible even the experiments which weren't possible before. And so, as I said, that we are able to measure several techniques together. I haven't said of how the correlative microscopy actually works with CPAM technology. So how does it work? CPAM is made possible by integration Lightscope into the SEM. It offers all-in-one solution for simultaneous analysis of multiple channels. Sorry for that. I hope it will work now. Yeah. Sorry for that. For simultaneous analysis of multiple material properties on the nanoscale. So during scanning, the electron beam points very close to the AFM tip. They both remain static while sample is moving thanks to the piezo scanner underneath. This way, data from both microscopes are acquired at the same time, same place, and under the same conditions. Simultaneous detection of various SEM and AFM signals enables a unique combination of data, such as atomic force microscope with topography with S and BSC contrast, resulting in the three-dimensional CPAM image, as you can see. This way, we can correlate different signals, such as electrical or magnetic properties. And so, as this technology is the most important one to understand, I have another scheme here one more time, that we have AFM probe and the electron beam, which points very close to each other. There is a slight offset, and we are measuring with the sample. We get at the same time the data from SEM and data from AFM. And so this way we correlate into one three-dimensional image. Control the measurement in the Nanoview software, which you can see now. And you can measure different signals and choose which one you need at the moment. So for instance, here are AFM topography, secondary electrons, and backscattered electrons, or error, and other possibilities. So if I can sum up the correlative microscopy, it enables us to simultaneously acquire AFM and SEM data and their precise correlation into 3D CPAM view. It provides more information than each imaging technique separately, and it actually provides us all-in-one AFM-in-SEM solution. Let's move to the Lightscope itself. As we were talking about the CPAM technology, let's have a look inside of Lightscope. First, the setup. we have the SEM microscope chamber. The Lightscope is sitting on the stage. We are connected to the nanobox controller, and we are measuring in the same computer as SEM1 in NanoView. So the integration of Lightscope takes 5 minutes, as the Lightscope is fixed to SEM stage by a few screws and connected to the controller by 2 cables. Then we place the sample and the AFM probe into Lightscope head, and we rotate in the convenient position. Finally, we close the chamber and we are ready for the measurement. As the Lightscope is designed for easy plug-and-play integration, the measurement is quite intuitive and simple. We can change the sample or probe as we need and precisely combine several measurement techniques. So, Lightscope integration into the SEM, there is easy adaptation mechanism. There is no need for rotational or other stage removals during Lightscope integration. And we are compatible with several different suppliers of scanning electron microscopes. And what are the Lightscope features and specifications? Lightscope is quite small and light. The dimensions are approximately 12 centimeters to 8 centimeters, and light it has half of the kilogram. The scan size can be up to 2 to 1 centimeter, and the sample height can be up to 8 millimeters. We provide different scanner configurations, either open or closed loop. And we are measuring with the self-sensing probes, which are operated up to 75 kilohertz, or you can use optionally lock-in amplifier. Lightscope has very high resolution. In XY direction, it's for fine surfaces approximately 20-25 nanometers. And the limit of Z direction is less than a nanometer, as you can see here in the graph. Lightscope enables multimodal characterization. We divide the techniques into 4 groups. The first one is material mechanical properties, such as topography measurement or local elastical properties. Second one is the material electrical properties, so we can measure the conductivity of the sample surface or local surface potential or IV curves at one point. Then there is a group which takes some of mechanical and electrical properties all together, and we have the piezo domain. So we measured piezoelectric domains, how they change in the material, and we are able to measure magnetic properties using MFM measurement. There are optional accessories which can be used with Lightscope or which are available. The first one is the nano case. It is a box where which you use if you'd like to measure not only in the vacuum in the chamber, but also as a standalone AFM. So you can control the atmosphere, you can use some gases or vacuum, and it prevents the vibrations in the office, for instance, if you don't want to measure in the lab. The second is the nano indenture module. This module is together with our partner Alumnis. It's a technology where we are able to measure nano indentation together with AFM capabilities in the SEM chamber. So there is quite precise indentation targeting, And so we can measure the indents, how it looks like and what happens there. Last year, we released the sample rotation. It has several, its benefit is that several samples or larger samples can be measured at once. Sample or other is for fib milling, for instance, that the sample can be oriented to the exact position where it's needed. And we can rotate back and forth as necessary. There are more. Last but not least is the load lock probe sample exchange. This mechanism is when you don't need to vent the chamber if you need changing the probe or changing the sample. And so I like to move to the application areas, as we were talking about the hardware of Lightscope. And so let's have a look on our application areas. We divide application areas to 4 different groups, such as material science, where we are able to measure one-dimensional or two-dimensional materials, steels and metal alloys, batteries, ceramic, etc. The second one is are nanostructures. We are able to modify surfaces and measure them. We are able to measure nanostructured films or patterning. The third one is semiconductor field, where we are measuring integrated circuits, solar cells, failure analysis, etc. And life sciences for cell, marine, or protein technology. So let's have a look at a few examples of these areas. And so let's have a look at material science. I have chosen an example from steels and metal alloys. In this field, multimodal analysis is necessary because alloys have quite interesting properties, and we have to understand in order to use them in the automotive industry, robotics, etc. So we can measure the topography, material contrast, surface potential, or mechanical properties in order to have them lighter and harder, for instance. Here is an example of biocompatible alloy. This mangan calcium zinc alloy is perspective for biodegradable materials with potential use in prosthetics. Complex in-situ analysis was done here in order to study the precipitation hardening. It's important to know the shape, size, and composition of the precipitate. So let's have a look. There was uneven surface, so only some of the islands were precipitates, but often we weren't sure which one is precipitate and which one not. So KPFM, the surface potential, is different on the precipitate. So KPFM was able to recognize them. So we measured in the SEM, AFM, and KPFM signal. And we were able to easily localize the islands. We were able to navigate to the area of interest, the probe, without risk of damaging the probe when the islands were big. And we were able to identify the precipitate using measurement of surface potential. Another example here is from battery research. Cathode powders are studied quite a lot because cathode active material can be used in the rechargeable batteries. So in order to prolong the battery lifetime, the powder particles needs to be protected by coating in order to not having the unwanted reactions. So we studied correlatively SEM, AFM, and conductive measurement. And as you can see on the images, the particles were quite different with different heights. So the navigation was necessary in SEM. And so we measured correlatively secondary electrons with topography and with conductivity map. And we found out that the coating was mainly conductive along the edges, as the detail shows. And so we were able to measure in situ the samples which are quite air susceptible, and they would otherwise oxidize if changed between the devices. And it was a quite time efficient analysis with the precise grain identification. If we have a look at the example from semiconductor field, semiconductor industry or research is quite important to know how to fabricate the samples and how to fabricate it without some defects and failures, or at least understand the leakages in the semiconductor devices. Another thing is to, as everywhere are nowadays use semiconductors, how to effectively analyze the data. And also it's quite important to know the surface potential. So optimized sample preparation and analysis is one of the case. And so if we are able to find the area of interest by secondary SEM microscope, we are able to FIP etch or polish the sample surface. And then we are able to analyze the structures. So, and it's everything what I said is under in situ conditions. So if we have a look at one example of defect analysis, it's, as I said, quite essential for fabrication and functionality of semiconductor structures to analyze the structures for defects. Here is an example of CMOS type chip, and we can see that the tungsten plugs were polished in cross-section, and then we see that the contact potential alternates. It wouldn't be possible to find it out in SEM or topography because it looks the same, but we need to know it in order to understand how the device works. I chose also one example or two examples in life sciences. So in life sciences, unique mechanical properties are studied in order to be used in the biomedical or drug delivery applications. Here is an example of polysaccharide fiber. It was measured in the cross section. So first, the sample, the fiber was cut by focused ion beam. And then we navigated in the tilt in SEM, and then we could do the AFM measurement. So the navigation here, as you can see, was quite difficult. And so we are now in the contact, and we were able to measure the topography with energy dissipation. So now we are able to have a look inside of the fiber, how it looks like and what happens there. Another example from protein nanowires is when the Lightscope was used to measure hanging nanowires directly on the hydrophobic nanopillars. So dimensions, Young modulus, and tensile strength of the nanowires were established and were studied. So if we have a look, there is a AFM tip, and here is nanowire deformation. We were studying both the elastic deformation and the plastic deformation. And at the same time, we were able to observe the nanowire life. And so if there is more what you'd like to see or know. We have more applications and product info. You can have a look at more information on our webpage. We have more application examples and application notes. Also, we have several modules and accessories. The product brochures and notes are there. We post on our social media regularly on LinkedIn, Facebook, and Twitter. And also we post the videos of products and webinars on our YouTube account, so you can have a look there. We have around the world, we have our local partners. As you can see, our office is here in the middle of the Europe. And if you'd like to talk to us face to face, you can meet us at the conferences. There are not all of the conferences. We have here only till the May. So if you will be on one of them, feel free to stop by and ask us, or you can just ask right now. We will answer. I'd like to summarize what we were talking today about. So we were talking about Lightscope, that it's high-speed, compact, and easy to use AFM-in-SEM. It's quite fast also to integrate the Lightscope into the chamber. AFM-in-SEM solution enables us to measure under in-situ conditions in the same place and under the same and at the same time. We are able to measure complexly several different signals, both from SEM and AFM, such as the chemical composition of the sample, material contrast, the electrical, mechanical, and magnetic properties. And also, it's quite fast and easy to localize the area of interest using these devices together. We were talking about the CPAM technology. It is the next level of correlative imaging with simultaneous data acquisition. And we were talking about our unique applications. They represent type of analyses which are not possible using standalone systems. And we were talking a bit about the different application fields from material science, nanostructures, semiconductors, and life sciences. And so we got into the questions and answers section. Here, I've chosen few of the questions which you had during the webinar, and I think they are that interesting that I should answer them aloud for more people. So the first question is the system compatible with all commercial available SEM stage systems? So in general, the system is compatible with all of them. Anyway, we didn't have opportunity to check them in all. So if you want to check if your SEM, please contact us and we will answer you. Or we will have to try maybe. So the second question is, does it work? Does this work in air, or it can be work in vacuum or in liquid media too? So in air and vacuum, there are no problems. In liquid media, we haven't tested it yet, so we'll see. The third question is, what would you say the order of magnitude is of the offset between SEM and AFM images? So the offset, it depends on how big the scan area is. So usually it's the least is 10% of the image, but we are able to go between in hundreds of nanometers, definitely. So is it also possible, it's the fourth question, is it also possible to get an SEM image at a higher magnification, for instance 100 as in the normal SEM? So as we are installing the Lightscope on the SEM stage, we don't influence any of the magnification in SEM, so you can go as much as you'd like. Okay, so these were the questions, and so with this I would like to thank you for your attention, thank you for your questions, and if you'd like to if you have any more questions now, you can type them, we will answer them now. And otherwise, let's see you on our next webinar. And thank you. Bye.